Somewhere in space, something sent a signal. Not noise, not random radiation, not the usual background whisper of the universe. Something precise, focused, and strangely intentional. It lasted just long enough to be noticed, and then it vanished, forever. And here's the unsettling part. Nearly half a century later, we still have no idea what it was. That moment was not just a curiosity. It was a warning, because since then, as our instruments have grown more powerful, space hasn't become clearer. It has become stranger. Signals that don't repeat. Stars that dim for no reason. Structures so vast they shouldn't have had time to form. It's almost as if the universe is quietly breaking its own rules. And tonight we're going to follow those cracks. Slowly, calmly, one mystery at a time. Welcome to Velarin's Sleepy Space Mysteries. If you've ever wondered what lies beyond the edges of what we understand, you might remember our journey into deep cosmic signals, the ones that drift through space like whispers without a source. Tonight's story feels connected to that, but far more unsettling, because this time we're not just listening, we're noticing patterns. So before we drift deeper into the unknown, take a moment to subscribe, gently like the video, and turn on the bell so you don't miss the next quiet mystery. If you enjoy these slow explorations, you can also support the channel through membership. And as always, tell me where in the world you're listening from tonight. Now, let's return to that signal. The one that appeared once and never came back. If you imagine space as quiet, empty, and predictable, then the story of that signal begins to gently undo that illusion. Because what happened in 1977 was not just unusual, it was deeply specific. A radio telescope, designed to listen passively to the sky, detected something that stood out instantly from everything else it had ever recorded. Not louder in a chaotic way, but cleaner, focused, as if it had been placed there deliberately, like a single note played in a silent room. The signal lasted 72 seconds, just over a minute, long enough to be confirmed, but too short to be understood. And when scientists examined it more closely, they noticed something quietly unsettling. It was centered around a frequency that nature itself seems to favor. A frequency tied to hydrogen, the most abundant element in the universe. This is not just any random part of the radio spectrum. It is what many scientists have long considered a kind of universal meeting point, a place where any intelligent civilization, regardless of its biology or origin, might choose to transmit. So naturally, the question formed almost immediately. If you wanted to be found, if you wanted to be heard across the vast emptiness of space, wouldn't you choose that exact frequency? And yet, despite decades of listening, that signal never appeared again. Astronomers returned to that exact region of the sky over and over again, using more advanced instruments, more sensitive receivers, more refined methods. They waited patiently, hoping for even the faintest echo. But the universe remained silent. Whatever produced that signal either stopped, moved, or was never meant to repeat in the first place. Now, there are explanations. There are always explanations. Some scientists suggest it may have been a natural event, perhaps a comet releasing hydrogen gas, briefly interacting with solar radiation in just the right way. Others consider the possibility of interference, a stray signal from Earth that somehow slipped through layers of filtering. But each explanation carries small inconsistencies, tiny details that don't quite align, because natural signals tend to spread across a range of frequencies. They are messy, blurred, like static. But this signal was narrow, extremely narrow, focused in a way that feels intentional. And that word, intentional, is where the discomfort begins. Because once you allow that possibility, even slightly, it opens a door that is difficult to close. If this signal was not natural, then it implies something else. Something capable of choosing a frequency, choosing a direction, and sending a message across light years of darkness. But then comes the quieter, more unsettling question. Why only once? If it was a message, why not repeat it? If it was a beacon, why not sweep the sky again? Unless, perhaps, it wasn't meant for us at all. Perhaps we simply drifted through its path, like standing briefly in the beam of a distant lighthouse that continues turning, unaware of who might be watching. And this is where the mystery begins to stretch beyond a single event. Because the deeper we look into space, the more we encounter things that behave like this. Not chaotic, not random, but strangely incomplete. As if we are only ever seeing fragments of larger processes, catching moments that were never designed to be fully understood from our position. The signal becomes less of an isolated curiosity and more of a pattern, a hint that space may not be as continuously observable as we assume, that some phenomena may appear briefly, then disappear, leaving behind only questions. And as we move forward, you'll start to notice something quietly consistent. These mysteries rarely repeat. They don't give us time to study them properly. They appear just long enough to be undeniable, and then they're gone, which forces us into a strange position. We are trying to understand a universe that does not always allow itself to be observed twice. And that idea begins to change everything. Because if space only reveals certain events once, then how many others have we already missed? Or more quietly, how many are happening right now, just outside the narrow window of our attention, waiting to be noticed for a single moment before vanishing again into silence? If that signal was the first quiet crack in our understanding, then what came next felt less like a crack, and more like a slow bending of reality itself. Because years later, astronomers began watching a star that behaved in a way no star should. Not violently, not explosively, but subtly, unpredictably, as if something unseen was passing in front of it, over and over again, without pattern, without rhythm, without explanation. First, nothing seemed unusual. Stars dim all the time. When a planet crosses in front of a star, it blocks a small fraction of its light. This is one of the most reliable methods we use to discover distant worlds. The dimming is usually tiny fractions of a percent, and most importantly, it is consistent. The same dip repeating at the same interval, like a clock ticking across space. But this star refused to behave like a clock. Its light didn't dip gently, plunged. 15%, sometimes more than 20% of its brightness simply disappeared, then returned, then disappeared again with no predictable timing. Days, months, even years could pass between these events. And each time the pattern was different. To understand how strange this is, imagine our own sun suddenly losing a fifth of its brightness without warning, and then returning to normal as if nothing had happened. There is no known planet that could cause such a massive drop. Even a giant like Jupiter would only block a tiny fraction of a star's light. What we were seeing required something enormous, something irregular, something that did not follow the neat orbital patterns we expect. And so, slowly, carefully, astronomers began proposing possibilities. Perhaps it was a swarm of comets, hundreds, maybe thousands of them, drifting in chaotic orbits, releasing dust that intermittently blocked the star's light. It sounded reasonable at first. Comets can create uneven shadows. Their tails can scatter light in complex ways. But the deeper they looked, the less it fit, because such a massive swarm would produce heat, detectable in infrared wavelengths, and that heat simply wasn't there. It was as if something was blocking the light without leaving the thermal signature it should have. Then came another idea: collision. Two large bodies smashing together near the star, creating a cloud of debris that slowly spread out, occasionally passing between us and the star. But again, the evidence didn't align. The expected dust signatures, the gradual dissipation patterns, they were missing or inconsistent. And so, almost reluctantly, a more speculative thought entered the conversation. Not as a conclusion, but as a placeholder for the unknown. What if whatever was causing this dimming wasn't natural in the way we understand nature? It's important to stay grounded here. Most scientists do not believe the star is surrounded by artificial structures. But what matters is not the conclusion. It's the fact that the data forced the question to be asked at all. When observations push you to consider ideas that once felt unnecessary, it means something deeper is happening. Over time, more detailed observations revealed a subtle clue. The dimming affected different colors of light in slightly different ways. Blue light was reduced more than red light, suggesting that fine particles, perhaps dust, were involved after all. But this only shifted the mystery. It didn't resolve it, because now the question became, where is this dust coming from? And why does it behave so irregularly? The leading idea today is that the star may be surrounded by a vast, uneven field of debris, possibly the remains of a shattered planet or a catastrophic event we didn't witness. Fragments drifting slowly, unpredictably, occasionally aligning just enough to block significant portions of starlight. But even this explanation feels incomplete, because despite years of observation, the pattern has not settled into anything predictable. The star continues to dim in ways that feel almost spontaneous. And this brings us back to that earlier thought, the one we began forming with the signal. What if we are only seeing fragments? What if space is full of processes that do not repeat on human timescales, or do not repeat in ways we recognize? This star, like the signal before it, offers us something undeniable, but not enough to fully understand it. It shows us the effect, but hides the cause just beyond reach. And slowly, almost imperceptibly, a pattern begins to form, not in the data itself, but in the nature of these mysteries. They appear, they challenge expectation, they resist explanation, and then they continue just out of sync with everything we know, which leads to a quiet realization, one that doesn't arrive all at once, but settles in gradually. Maybe space isn't behaving strangely. Maybe it has always behaved this way, and only now, for the first time, we are beginning to notice. By now, a quiet pattern is beginning to take shape. Not a pattern of answers, but a pattern of behavior. Signals that appear once and vanish. Stars that dim without rhythm. Phenomena that resist repetition, as if the universe reveals them only briefly, then closes the door again. And just as this pattern starts to settle into the background of our thinking, something even stranger emerges. Not a signal, not a star, but a structure, vast, circular, and so unexpected that when astronomers first saw it, they assumed it had to be a mistake. These structures are known quite simply as odd radio circles, and the name is not an exaggeration. When observed through radio telescopes, they appear as enormous, nearly perfect rings floating in space. Not faint distortions, not irregular clouds, but clean, defined circles, stretching across distances so large that light itself would take hundreds of thousands, even millions of years to cross them. At first, the reaction was skepticism. In astronomy, perfect shapes are suspicious. Nature rarely produces clean geometry on such massive scales. Circles, especially, tend to signal something artificial in data processing. A glitch, a miscalibration, a pattern created by the instrument rather than the universe itself. So the initial assumption was simple. There must be an error somewhere in the system. But when the data was checked, and then checked again, the circles remained. Different observations, different angles, different instruments, all confirmed the same thing. These rings were real. They existed in space, and they were not small. Some of them are so large that they dwarf entire galaxies, expanding far beyond anything we typically associate with a single cosmic event. And at the center of many of these circles, there is something quietly ordinary. A galaxy, not particularly unusual, not violently active, just a typical galaxy, sitting at the center of something that should not exist around it. Naturally, astronomers began searching for familiar explanations. Could these be the remnants of massive explosions? When stars explode as supernovae, they can create expanding shells of gas that sometimes appear circular. But those remnants are relatively small, and they fade over time. These radio circles are far larger and persist in ways that don't match supernova behavior. What about the powerful jets emitted by supermassive black holes? Some galaxies shoot streams of high-energy particles into space, creating vast lobes of radio emission. Under certain conditions, these can appear somewhat circular. But again, the details don't align. The galaxies at the centers of these circles don't show the kind of activity required to produce such enormous, symmetrical structures. So once again, the explanations begin to stretch. Perhaps these are shock waves, ancient echoes from events that happened millions of years ago. A burst of energy expanding outward, forming a shell that we now detect as a ring. It's a possibility, but if that were the case, we should see many more of them. Galaxies are not quiet places. They experience bursts of activity, collisions, and energetic events all the time. And yet, these circles are rare, exceptionally rare, and that rarity makes them even more difficult to understand, because it suggests that whatever creates them is not a common process. It is something unusual, something that happens under very specific conditions, or perhaps something we have not yet identified at all. There are more speculative ideas as well, concepts that reach into the edges of theoretical physics. Some have wondered whether these circles could be linked to large-scale phenomena from the early universe, remnants of processes that occurred shortly after everything began. Others have suggested connections to hypothetical structures in space-time itself, features that we have not yet observed directly, but which could leave imprints on the distribution of matter and energy. These ideas are not widely accepted, but their existence tells us something important. When observations cannot be explained within existing frameworks, the boundaries of those frameworks begin to expand. Scientists are forced to consider possibilities that once felt unnecessary, not because they want to, but because the data leaves them no choice. And once again, we find ourselves in a familiar position. We are observing something real, something measurable, something that clearly exists, but we do not understand what it is. The circles remain silent, immense, and almost perfectly shaped, as if drawn across the fabric of space itself. They do not change quickly. They do not reveal their origin easily. They simply persist, waiting for an explanation that has not yet arrived. And when you place them alongside everything we've already seen, the signal, the star, the irregular patterns, a quiet thought begins to surface again. What if these are not separate mysteries? What if they are different expressions of the same underlying truth? That space is not as simple as we once believed. Because each time we look deeper, we don't just find new objects. We find new behaviors. And those behaviors are beginning to feel less like exceptions and more like clues. By this point, something subtle has begun to shift in the way we think about space. It no longer feels like a place where everything follows clear, repeatable rules. Instead, it starts to feel layered, as if beneath the familiar patterns we've studied for decades, there exists a deeper level of structure that only reveals itself occasionally and never in full. And just as this idea begins to settle, we encounter something that challenges not just individual observations, but one of the most fundamental assumptions about the universe itself. Because for a very long time, cosmology has relied on a quiet principle. A kind of background belief that, on the largest scales, the universe is roughly the same everywhere. Not identical in detail, of course, but balanced, uniform. If you zoom out far enough, the distribution of galaxies should look evenly spread, like a fine mist stretching in all directions. This idea is known as the cosmological principle, and it underpins nearly everything we think we know about how the universe formed and evolved. But then, astronomers began to notice something that didn't quite fit. At unimaginable distances, billions of light years away, they found structures so vast that they seemed to stretch the limits of what should be possible. Not clusters, not filaments, but enormous arrangements of galaxies forming shapes that appear coherent, connected, almost as if they belong to something larger than random distribution. One of these structures spans over 3 billion light years. Not the distance to it, but its actual size. To visualize that, imagine a beam of light starting at one end. It would take 3 billion years just to reach the other side. This is not just large. It is so large that it begins to conflict with the idea that matter should not have had enough time to organize itself into something this extensive since the beginning of the universe. And then, in the same region of space, another structure appears, slightly smaller, but still enormous. A kind of ring or loop composed of galaxies that seem to trace a boundary across space. Two structures, in the same location, at the same distance, both pushing against the limits of what our models predict. Naturally, the first response is caution. Human perception is good at finding patterns, even where none exist. When we look at scattered points, our minds instinctively connect them, forming lines, shapes, arcs. So one possibility is that these structures are not truly coherent, but simply the illusion of alignment, a coincidence stretched across cosmic scales. But when scientists analyze the data statistically, the probability of these arrangements being random becomes very small. Not impossible, but unlikely enough to raise concern. Because if they are real, then something in our understanding is incomplete. And this is where the tension quietly deepens. Because the cosmological principle is not a minor detail. It is a foundation. It shapes how we interpret the expansion of the universe, how we model the growth of structure, how we trace the history of everything from the first atoms to the largest galaxy clusters. If that foundation begins to shift, even slightly, then many of the conclusions built upon it may need to be reconsidered. There are attempts to explain these structures within existing theories. Some suggest they may be related to early fluctuations in the density of matter, tiny variations that were amplified over billions of years. Others point to wave-like patterns in the early universe, echoes of pressure moving through the primordial plasma shortly after the beginning of everything. These processes can create preferred scales, subtle imprints in how galaxies are distributed. But once again, the details resist alignment. The sizes of these structures exceed what those mechanisms comfortably produce. They are larger, more extended, more organized than expected. And so, gently, almost reluctantly, a deeper question begins to emerge. What if the universe is not as uniform as we assumed? Not chaotic, not random, but uneven in ways that only become visible at the largest possible scales. Like a fabric that appears smooth from a distance, but reveals hidden patterns when examined more closely. This does not mean everything we know is wrong. It simply suggests that our current models may be incomplete, that there are layers of structure we have not yet accounted for, processes that operate beyond the limits of our current understanding. And when you place this alongside everything we've already explored, the signal, the dimming star, the perfect circles, a quiet realization begins to settle more firmly. These are not just isolated anomalies. They are pressures gently pushing against the boundaries of our knowledge. Each one on its own can be explained, or at least contained within uncertainty. But together, they begin to form a pattern that is harder to ignore. A pattern that suggests we are approaching the edge of something, not a boundary in space, but a boundary in understanding. And just beyond that boundary, there may be a version of the universe that behaves in ways we have not yet learned to recognize. And just when it begins to feel like we've reached the edge of how strange space can become, something even quieter, and in some ways more unsettling, comes into view. Not something enormous, not something explosive, but something defined by absence. A region of space so empty, so unexpectedly hollow, that it forces us to reconsider not just what exists in the universe, but what doesn't. This region is known as a cosmic void, and voids in general are not unusual. The universe, when mapped on large scales, resembles a vast web. Galaxies cluster along long filaments, forming intricate networks, and between those filaments lie enormous empty regions. These are the voids, the spaces where very little matter exists. They are part of the natural structure of the cosmos. But every now and then, we find a void that goes beyond what we expect. One such region stretches across hundreds of millions of light years. To give that scale a sense of weight, if our entire galaxy were placed inside it, it would feel almost alone, surrounded by distances so vast that even light would take millions of years to reach the nearest neighbors. And yet, based on our models, this region should not be so empty. Given the average distribution of galaxies in the universe, a space this large should contain thousands of them. Not densely packed, but present, scattered, visible. Instead, when astronomers observe this region carefully, they find only a few dozen. The rest is missing, not hidden, not obscured, simply absent. And this absence is not just a curiosity, carries weight, because the structure of the universe is shaped by gravity acting over time. In the early moments after the universe began, matter was distributed almost evenly, with only tiny fluctuations. Over billions of years, those small differences grew. Denser regions pulled in more matter, forming galaxies and clusters, while less dense regions lost matter, becoming voids. This process is well understood, simulated, modeled, tested repeatedly, and those models predict limits. They suggest how large voids can become, how empty they can be, given the age of the universe and the strength of gravity. This particular void sits very close to that limit, almost uncomfortably close. It is not impossible, but it is extreme, a kind of edge case, where everything aligns just enough to create a region that feels like it is pushing against the boundaries of what should naturally occur. And yet, it exists, quietly, persistently. But what makes this even more intriguing is not just the emptiness, but what little remains inside it. The few galaxies that do exist within this vast void behave differently. Some form stars at unusual rates. Others show characteristics that don't quite match their counterparts in denser regions. It is as if isolation itself is changing them, allowing them to evolve in ways that are rarely seen elsewhere. Imagine a galaxy drifting through space with almost no neighbors, no close interactions, no gravitational disturbances. It evolves slowly, quietly, untouched by the chaos that shapes most galaxies. Over time, that isolation may lead to behaviors we are only beginning to notice. And so, the void becomes more than just empty space. It becomes a kind of natural experiment, a place where the usual rules of interaction are removed, revealing how systems behave when left almost entirely alone. But the deeper question remains: why is it so empty in the first place? The answer likely traces back to the very beginning, to the smallest fluctuations in density that existed when the universe was still incredibly young. Tiny differences, almost imperceptible, that were stretched and amplified over billions of years. In most regions, those differences grew into the rich structures we see today. But in this region, the initial conditions may have been just slightly lower than average, enough for matter to drift away rather than gather. And over time, that slight imbalance became an enormous absence, a reminder that even the smallest variations, given enough time, can lead to the largest consequences. And once again, the pattern returns. A signal that appeared once, a star that dims without reason, circles that should not exist, structures too large to form, and now a region too empty to ignore. Each one different in detail, but similar in feeling. They do not break reality outright. They lean against it, gently, persistently, suggesting that what we understand is only part of a larger picture. And as we move forward, that picture will become even more complex. Because next, we are going to look not at space as it exists today, but at the oldest light in the universe and the strange imprint hidden within it. Before we continue, if you're still listening, gently let me know by commenting 1. It's a small signal, but unlike the ones we've been exploring, this one will come back. If everything we've explored so far feels strange, signals that vanish, stars that dim without rhythm, structures that stretch beyond expectation, then what you're about to hear is something even quieter and yet far more profound. Because now we are no longer looking at objects within the universe. We are looking at the universe itself, as it was when it was still young, still forming, still almost perfectly uniform. There is a faint glow that fills all of space. You cannot see it with your eyes, but it is everywhere, in every direction, surrounding us completely. It is the oldest light we can observe, a kind of afterglow left behind from a time when the universe was only a few 100,000 years old. Compared to its current age of nearly 14 billion years, that moment was almost the beginning. This ancient light is incredibly uniform. No matter where we look, it is almost exactly the same temperature, a soft, even background that suggests the early universe was remarkably smooth. But not perfectly smooth. There are tiny variations, incredibly small differences in temperature, so subtle that they are measured in fractions of a fraction of a degree. And those tiny variations are everything. They are the seeds from which all structure grew. Every galaxy, every cluster, every void, all of it traces back to these faint fluctuations in the early universe. By studying them, scientists can understand how the cosmos evolved from a nearly featureless state into the complex structure we see today. But hidden within this ancient light, there is something that does not quite belong. A region that is noticeably colder than it should be. Not dramatically colder, but significantly enough to stand out against the delicate balance of the surrounding background. And in a map where almost everything is uniform, even a small deviation becomes meaningful. This region spans a vast area of the sky. If you could see it directly, it would appear many times larger than the full moon. A wide, gentle patch where the temperature dips slightly below what our models predict. And while the difference may seem small, within the context of this incredibly uniform background, it is unusually large. Statistically, it shouldn't really be there, or at least, it shouldn't be so pronounced. Now, there are explanations. There are always explanations. One idea suggests that between us and this ancient light, there may be a large region of emptiness, a void similar to the one we discussed earlier. As light travels through such a region, it can lose a small amount of energy due to the way space expands over time. This would cause the light to appear slightly cooler when it reaches us. It's a subtle effect, but measurable. And indeed, astronomers have found evidence of a relatively large empty region in that direction. But here's where the mystery deepens. Even when that void is taken into account, it doesn't fully explain the coldness we observe. Contributes, but not enough. There is still a gap between what we expect and what we see. And so once again, the explanations begin to stretch. Some suggest that this cold region could simply be a statistical anomaly, a rare fluctuation unlikely, but not impossible. If you imagine running the universe many times with slightly different initial conditions, perhaps in a small number of those versions, something like this would appear. But we don't have many universes to compare. We have one. And in this one, the anomaly is real. Others have proposed more exotic possibilities. Ideas that reach beyond the boundaries of our current understanding. Concepts where our universe may not be alone, where interactions between different regions of space, or even different universes, could leave subtle imprints in this ancient light. These ideas are highly speculative. There is no direct evidence for them beyond the anomaly itself. But their presence in scientific discussion reveals something important. When conventional explanations fall short, even slightly, the door opens to possibilities that once seemed unnecessary. And once again, we find ourselves in a familiar position. We are observing something that clearly exists, something that can be measured, mapped, studied in detail, but we cannot fully explain it. The cold region remains quiet, ancient, embedded in the oldest light we can see. It has been there for billions of years, untouched, unchanged, a subtle irregularity in a universe that is otherwise remarkably consistent. And when you place it alongside everything we've already explored, the signal, the dimming star, the radio circles, the massive structures, the empty void, a deeper pattern begins to emerge. Not a pattern of shape or location, but a pattern of limitation. Each mystery exists just beyond the edge of what we can fully explain. Not completely unknown, but not fully understood. As if the universe allows us to see just enough to realize how much we are still missing. There is something quietly unsettling about the idea that the oldest light in the universe, the very first light we can observe, already contains an imperfection we cannot fully explain, because it suggests that whatever is incomplete in our understanding today may have been present from the very beginning, not as a later complication, but as something woven into the structure of the universe itself. And as we move forward from that ancient imprint, we return again to the present, to objects and events that feel closer, more tangible, but no less strange. Because now, instead of looking at the universe as a whole, we begin to focus on individual stars again. And one of them behaves in a way that challenges something far more fundamental than structure or distribution. It challenges the rules of matter itself. This star appears, at first glance, completely ordinary. Its size, its brightness, its temperature, all fall within the expected range for a star of its type. Nothing about it stands out when viewed casually. But when astronomers analyze its light more carefully, breaking it into its component colors, they uncover something that should not be possible. Embedded within that light are signatures of elements that should not exist there. Not just rare elements, but unstable ones. Elements that decay over time, sometimes very quickly. Elements that, under normal circumstances, would disappear long before a star reaches the stage of life this one is currently in. To understand why this is so strange, imagine placing a fragile substance in a harsh environment, one where it cannot survive for long. Over time, it breaks down, fades away, leaving no trace. Now imagine returning billions of years later and finding that substance still present, as if it had just been created. That is what this star presents to us. The elements detected within it have lifetimes that are incredibly short on cosmic timescales. Some decay in millions of years, which in the life of a star is almost nothing. And yet, this star is not young. It has existed for billions of years. Any such elements present at its formation should have vanished long ago. But they haven't. They are still there, consistently observed, not as a one-time anomaly, but as a persistent feature, which leads to a deeply uncomfortable question. Where are they coming from? One possibility is that the star is somehow producing these elements continuously, replenishing them as they decay. But this would require nuclear processes that we do not currently understand. The outer layers of a star, where these elements are observed, are not hot enough to create them through known reactions. The conditions simply don't allow for it. Another idea suggests that material from deeper within the star might be rising to the surface, carrying these elements upward. But again, the internal environment of the star does not support the formation of these particular elements in the necessary quantities. The explanation begins to stretch, requiring adjustments to processes we thought were well understood. And then, there are the more speculative possibilities. Ideas that suggest the presence of unknown forms of matter or exotic elements that exist beyond what we have observed in laboratories. Concepts that hint at regions of stability in the structure of atoms that we have not yet reached, where certain heavy elements might persist longer than expected, slowly decaying and producing the signatures we detect. These ideas remain unconfirmed. They exist at the edges of theory, not yet grounded in direct evidence. But once again, they arise because the observations leave us with no simple answer. And this is where the pattern returns, stronger than before. We are not dealing with a single anomaly. We are dealing with a repeated experience, a signal that appears once, a star that dims unpredictably, structures too large to form, voids too empty to ignore, ancient light that carries unexplained imprints, and now a star that seems to defy the expected behavior of matter itself. Each one on its own could be dismissed as an edge case, a rare occurrence, a statistical outlier, but together, they begin to form something more significant. They suggest that our understanding is not wrong, but incomplete. That the rules we rely on, while accurate within certain limits, may not apply universally in the way we assume. That there may be layers of physics, layers of behavior, that only reveal themselves under specific conditions we are only just beginning to encounter. And perhaps most quietly of all, they suggest that the universe is not obligated to behave in ways that are convenient for us to understand. It does not repeat every event. It does not reveal every process. It does not provide complete explanations. Instead, it offers glimpses, moments where something unusual becomes visible, just long enough for us to notice, and then fades back into complexity. And as we continue, the next mystery will take us even further beyond our own star system, beyond the familiar paths of planets and comets, into something that arrived from elsewhere, something that passed through our cosmic neighborhood and left behind more questions than answers. There is something different about an object that does not belong. Not something that formed here, evolved here, followed the slow, predictable rhythms of our solar system, but something that arrived from elsewhere, already shaped, already carrying a history we cannot trace. And for a brief moment, not long ago, one such object passed through our cosmic neighborhood. At first, it didn't seem extraordinary. Just another faint point of light moving across the sky. Astronomers are used to this. Asteroids drift through the solar system constantly, small remnants left over from its formation. Comets follow long, looping paths, occasionally visiting the inner planets before returning to the distant edges. Everything follows patterns, orbits that can be calculated, paths that can be predicted. But this object didn't follow a closed path. It came in fast, from outside the solar system, curved slightly as it passed near the sun, and then continued outward again, never to return. This trajectory was not bound to our star. It was not part of our system. It was a visitor, the first confirmed interstellar object ever observed passing through our solar system. And already, that alone is remarkable, because it means that objects drift between stars, quietly crossing the vast distances of space, occasionally passing through systems like ours without warning. But what made this object truly strange was not just where it came from, but how it behaved. As astronomers studied it, they noticed something unusual about its shape. Based on the way its brightness changed over time, flickering slightly as it rotated, they estimated that it was extremely elongated, not roughly spherical like most asteroids, but stretched, thin, almost like a shard. Some interpretations suggested it might even be flattened, more like a disk than a rock. Either way, it was unlike anything commonly seen in our solar system. But that was only the beginning. As it moved away from the sun, something subtle happened. The speed increased slightly more than expected. Not dramatically, not enough to be obvious at first, but enough that precise calculations began to show a mismatch. Gravity alone could not account for its motion. Something else was gently pushing it. Now, this kind of behavior is not entirely unfamiliar. Comets often accelerate as they heat up near the sun. Ice turns into gas. Jets of material escape, and the object experiences a small thrust, like a natural rocket. But comets also produce visible signs: a glowing coma, a tail stretching away from the sun. This object showed none of that. No visible gas, no dust cloud, no tail, just a smooth, silent passage, accompanied by a slight, unexplained acceleration. And once again, the explanations begin to stretch. Perhaps it was releasing gas in a way we couldn't easily detect, something more subtle than typical comet behavior. Maybe the material escaping was transparent, or too faint to observe with the instruments we had at the time. This is still considered the most likely explanation, but even this leaves questions, because the acceleration was consistent, smooth, not erratic. It suggested a steady push, rather than irregular bursts. And that brings us to another possibility, one that feels simple at first, but becomes more complex the longer you think about it. Light itself can push objects. Every photon carries a tiny amount of momentum. When light from the sun strikes a surface, it exerts a small pressure. For most objects, this effect is negligible, far too weak to matter. But if an object is very thin or very light with a large surface area, that pressure can become noticeable. So perhaps this object was not dense like rock, but something lighter, something more like a sheet, a thin structure that could be gently accelerated by sunlight alone. And this is where the speculation begins to deepen, because natural processes do not easily create large, thin, rigid structures in space. It is difficult to imagine how such a shape would form, how it would survive, how it would travel between stars without breaking apart. The idea is not impossible, but it is unusual enough to invite more imaginative explanations. Some have suggested that it could be artificial, a fragment of something constructed, perhaps a kind of sail designed to move through space using light itself. This idea is not widely accepted and remains highly speculative. But once again, it appears not because scientists want it to be true, but because the observations leave space for it. And then, just as quickly as it arrived, the object was gone. It moved beyond the reach of our telescopes, fading into the darkness between stars. We had only a short window to observe it, to measure it, to try to understand it. And that window closed before we could gather all the data we needed. So now it remains a mystery, a visitor from another star system, carrying information we could not fully extract, behaving in ways we could not completely explain, and leaving behind only questions. And once again, the pattern holds: a brief appearance, a measurable anomaly, an incomplete explanation, then silence. And as we continue, the next mystery will not drift quietly through space. It will explode into it, faster, brighter, and more unexpectedly than anything we thought possible. If the visitor from interstellar space felt quiet, almost subtle in its strangeness, then what came next was the opposite. Not silent, not gentle, but sudden, intense, and almost overwhelming in its brightness. Because sometimes the universe does not whisper its mysteries. Sometimes it flashes them into existence and then removes them just as quickly. In 2018, telescopes around the world detected a burst of light from a distant galaxy. At first, it seemed familiar. Astronomers have seen countless stellar explosions before. When a massive star reaches the end of its life, it can collapse and explode, releasing enormous energy in what we call a supernova. These events are powerful, but they follow patterns. They brighten over time, peak, and then slowly fade across weeks or even months. But this event did not follow that pattern. It became bright almost immediately. Within just a few days, it reached an intensity far greater than a typical supernova. Not just slightly brighter, but many times more luminous. And then, just as quickly, it began to fade. Not gradually, but rapidly, as if the energy that powered it had been released all at once, and then exhausted. It was like a sudden flash in the darkness, brilliant, brief, and completely unexpected. And as astronomers began to study it more closely, the details became even more unusual. The temperature of the explosion was extremely high, far beyond what we normally observe in similar events. The material seemed to be expanding at incredible speeds, a significant fraction of the speed of light, suggesting an immense amount of energy had been concentrated into a very short moment. Nothing about it fit neatly into existing categories. It wasn't behaving like a standard supernova. It didn't match known patterns of stellar collapse. It didn't evolve in the way models predicted. So once again, the process began. Observation, confusion, and then a search for explanation. One possibility is that this event marked the birth of something extreme. When a massive star collapses, its core can form either a neutron star or a black hole. In some cases, the energy released during this collapse may be channeled in unusual ways, perhaps forming jets that burst through the outer layers of the star, releasing energy far more quickly than expected. This could create a bright, fast event, something that rises and fades much more rapidly than a traditional explosion. Another idea suggests a more violent interaction. Imagine a star drifting too close to a black hole. The intense gravitational forces stretch it, pull it apart, tearing it into streams of matter that spiral inward. As this material falls toward the black hole, it heats up, emitting intense radiation. These events are known, but they usually unfold over longer timescales. What we observed here was much faster, more compressed, as if the process had been accelerated. There are also scenarios involving collisions. Dense stellar remnants, like white dwarfs or neutron stars, interacting in ways that release enormous energy in a very short time. These interactions are rare, but not impossible, and they could produce bursts of light that behave differently from anything we've seen before. But here's the deeper issue. Each explanation works partially. Each one captures some aspect of the event: the brightness, the speed, the temperature, but none of them fully explains all of it at once. There is always a gap, a small inconsistency, a detail that doesn't quite fit, and that gap is where the mystery lives. Over time, astronomers began to realize that this event was not alone. Similar flashes, rare but real, have been detected in other parts of the sky. They form a new category, something we didn't even know existed before. Fast, bright, short-lived events that appear suddenly and vanish before we can fully understand them. And once again, the pattern returns. A phenomenon appears clearly measurable, undeniably real, but just outside the boundaries of our current understanding. It doesn't break physics outright. It stretches it, gently but persistently, forcing us to reconsider what we thought we knew. And perhaps what is most striking about these events is not just their intensity, but their timing. They are brief, fleeting. They do not give us the luxury of prolonged observation. By the time we recognize what we are seeing, it is already fading, which leaves us, once again, with incomplete information. A flash, a measurement, a set of data points, and then silence. And as these patterns accumulate across signals, stars, structures, and now explosive events, a quiet realization begins to deepen. The universe is not withholding information deliberately, but it is not presenting it in a way that is easy to understand. Instead, it reveals itself in fragments, moments of clarity surrounded by vast regions of uncertainty. And as we move into the final part of this journey, the next mystery will challenge something even more fundamental. Not how objects behave, not how structures form, but how time itself is measured. Because what we are about to encounter is a star that appears to be older than the universe. There is something deeply unsettling about the idea of time being wrong. Not slightly off, not mismeasured by a small margin, but fundamentally inconsistent with everything we believe about the universe. Because time, more than anything else, is the framework that holds our understanding together. It tells us how long stars live, how structures form, how the universe evolves from its beginning to now. And yet, there exists a star that quietly challenges that framework. At first glance, it seems unremarkable. A dim point of light, relatively close in cosmic terms, sitting within our own galaxy. It is not particularly large, not especially bright, just an aging star that has moved beyond the earliest phase of its life. But when astronomers began to measure its properties carefully, something didn't quite align. Its composition suggested it formed very early in the history of the universe. It contains very few heavy elements, the kind that are created over time as generations of stars live and die. This scarcity tells us that it must have formed before those elements became common, in a much younger universe. So far, that makes sense. But when scientists tried to estimate its age more precisely, using models based on how stars evolve, how they burn their fuel, how their brightness and temperature change over time, they arrived at a number that felt uncomfortable. The star appeared to be around 14 billion years old. And that is where the problem begins. Because the universe itself, according to our best measurements, is only about 13.8 billion years old. That number is not uncertain in the way it once was. It has been refined through multiple independent observations, the expansion of space, the ancient background light, the behavior of distant galaxies. Everything points to roughly the same age. So how can a star be older than the universe it exists within? First, the answer seems simple. The measurement must be wrong. Somewhere in the process, an assumption has failed. A value has been misestimated. A model needs adjustment. And in many cases, that is exactly what happens. Science corrects itself, refines its methods, narrows its uncertainties. But this star has been studied carefully, repeatedly, with increasingly precise instruments. Its distance has been measured using subtle shifts in its apparent position as Earth orbits the Sun. Its brightness has been analyzed in detail. Its composition has been examined through its spectrum. Each refinement brings the estimate closer, but not comfortably so. The age remains uncomfortably high, not definitively older than the universe, but close enough that it presses against that boundary again and again. And that is where the tension lives. Because if the star truly is that old, then something in our understanding of time, or stellar evolution, or cosmic history must be incomplete. Not necessarily wrong, but missing a piece. A factor that shifts the calculation just enough to resolve the contradiction. There are possibilities. Perhaps our models of how stars age, especially those with very low amounts of heavy elements, are slightly off. Maybe these stars burn their fuel differently, more slowly, extending their lifetimes beyond what we expect. Or perhaps the measurements of distance, even though precise, still carry small uncertainties that influence the final calculation. There is also the possibility that this star formed extremely early, almost immediately after the first generation of stars lived and died, leaving behind just enough heavy elements to create a second generation like this one. In that case, it could be nearly as old as the universe without exceeding it. But even this explanation feels tight. It leaves very little room for error, very little margin for comfort. And so, once again, we are left with a familiar pattern, an observation that is real, a measurement that is consistent, an explanation that almost works, but not entirely. And in that small gap, the mystery remains. Because this is not just about one star. It is about the limits of our models, the assumptions we rely on when we interpret the universe. It is a reminder that even when everything seems well understood, there can still be edges, places where the data presses against the boundaries of what we think is possible. And when you step back and look at everything we've explored so far, the signal, the dimming star, the perfect circles, the impossible structures, the ancient cold imprint, the interstellar visitor, the sudden cosmic explosion, and now, a star that seems too old, a quiet realization begins to settle. These are not random curiosities. They are signals of incompleteness, not failures of science, but invitations, each one pointing gently towards something we have not yet fully grasped. And as we move into the final part, we will begin to bring these pieces together, not to force a single answer, but to understand what they might be telling us collectively about the nature of space itself. Before we continue, if you're still listening, gently let me know by commenting too, a quiet confirmation that you're still here, drifting through these mysteries, one layer at a time. By now, the pattern is no longer subtle. It has been building quietly across everything we've seen. Signals that appear once, stars that behave unpredictably, structures too large, voids too empty, ancient light with unexplained imprints, objects that pass through our system without belonging, and explosions that arrive and vanish before we can understand them. Each one on its own can be explained, or at least approached with theory, but together, they begin to feel connected. Not by cause, but by implication. They all suggest the same thing, that the universe, as we understand it, is incomplete, not broken, not chaotic, but deeper, layered, and still partially hidden from us. And this is where the final part of our journey begins, not with a new mystery, but with a different way of looking at all of them. Because instead of asking what each phenomenon is, we begin asking what they are telling us collectively. If you imagine our current understanding of the universe as a map, it is detailed in many places. We know how stars form, how galaxies evolve, how gravity shapes structure over time. We can predict orbits, measure distances, trace the expansion of space itself. The map works. It guides us. It explains much of what we observe. But every mystery we've explored sits at the edge of that map, not in the center where everything is well understood, but at the boundaries where the lines begin to fade. And what's interesting is that these edges are not random. They appear in specific places where our models rely on assumptions that may not hold universally. Take repetition, for example. Much of science depends on observing something more than once. We identify patterns, confirm behavior, refine our understanding through repeated measurement. But many of these cosmic phenomena do not repeat. The signal appeared once. The interstellar object passed through once. The explosion flared briefly, then disappeared. Even the dimming of that strange star, while ongoing, refuses to settle into a predictable cycle. This lack of repetition creates a kind of observational limit. It means we are often working with incomplete data, trying to understand processes that we cannot watch unfold again under controlled conditions. And that alone introduces uncertainty, not because the universe is unclear, but because our window into it is narrow. Then there is scale. Some of the structures we've discussed are so large, so vast, that they challenge the timelines we rely on. According to our current models, there simply hasn't been enough time since the beginning of the universe for matter to organize itself into such enormous forms. And yet, they exist, which suggests either that our understanding of how structure forms is incomplete, or that there are processes at work that we have not yet fully recognized. And then, there is behavior. Stars that contain elements that should not exist. Light that carries imprints we cannot fully explain. Objects that accelerate in ways that stretch our understanding of motion. Each of these observations hints at mechanisms, subtle processes, that operate just beyond the reach of our current theories. None of this means our models are wrong. It means they are unfinished, because this is how science has always progressed, not by replacing everything at once, but by expanding gradually as new observations reveal gaps in what we thought we knew. The anomalies come first, the explanations come later, and in between, there is a period like this one, where the mysteries accumulate, waiting to be connected. And that brings us to a quiet possibility. What if these phenomena are not isolated at all? What if they are different expressions of the same deeper layer of reality? One that we have not yet fully described. Not something dramatic, not a complete rewrite of physics, but an extension, a refinement, a new piece added to the framework that allows all of these observations to fit together more naturally. Because if you look closely, there is a shared characteristic across all of them. They occur at extremes. At the largest scales, structures become too big. At the emptiest regions, space becomes too empty. At the smallest fluctuations, ancient light becomes slightly too cold. At the edges of behavior, stars and objects act just slightly outside expectation. It is as if the universe behaves exactly as predicted until you reach its limits. And at those limits, something new begins to emerge. Something subtle, but consistent, a suggestion that the rules we rely on may be approximations, accurate within a certain range, but not absolute. And this idea is not unfamiliar. It has happened before. Newton's laws described motion perfectly, until we reached extreme speeds and strong gravity, where relativity took over. Classical physics explained energy and matter until we looked closely at the smallest scales, where quantum mechanics revealed a deeper layer of behavior. Each time, the old rules were not discarded. They were expanded. And perhaps that is where we are now, standing at the edge of another expansion, surrounded by clues, but not yet seeing the full picture. If what we are sensing is real, if these anomalies are not isolated but part of a larger pattern, then the next question becomes quietly unavoidable. What exactly is missing from our understanding? Not in a dramatic sense, not something that overturns everything we know, but something subtle, a missing layer, a missing connection between the rules we already use. Because when you look closely, none of these mysteries completely violate physics. They don't shatter the laws of nature. Instead, they sit just at the edge, where those laws begin to blur. And that boundary is where the most important discoveries in science have always been made. Think about it this way. Every model we build is based on observations within a certain range. We study stars like our sun, so we understand how typical stars behave. We observe galaxies across billions of light years, so we understand large-scale structure. But when something appears outside those familiar ranges, something more extreme, more rare, our models are forced to stretch. And sometimes, they stretch just enough to reveal a gap. One possibility is that we are underestimating how dynamic the universe truly is. We often imagine cosmic processes as slow, gradual, unfolding over millions or billions of years. And in many cases, that's true. But what if there are layers of activity that operate on entirely different timescales? Processes that are brief, intense, and rarely repeated, making them difficult to observe in full? That would explain why so many of these phenomena appear suddenly and then disappear, not because they are rare in absolute terms, but because they are brief relative to our observation window. Like trying to understand lightning by watching the sky only once a day. You might miss most of it, and when you do see it, it feels unexpected. Another possibility lies in how we interpret cause and effect across vast distances. Light takes time to travel. When we observe distant objects, we are not seeing them as they are now, but as they were long ago. In some cases, millions or billions of years in the past. This means that what appears as a single, isolated event might actually be part of a longer process. One we cannot see in full because its different stages are separated across time and space. In other words, we may be observing fragments of much larger stories. A signal that appears once might be part of a repeating cycle that spans centuries or millennia. A dimming star might be influenced by structures or events that we cannot fully resolve from our distance. Even those enormous cosmic formations may be temporary arrangements, evolving slowly beyond the limits of our observation. And then, there is a deeper possibility, one that is more difficult to grasp, but quietly present in the background of modern physics. That the laws we use, while accurate, are not complete descriptions of reality, but approximations. This is not a new idea. It has happened before. The physics that describes everyday motion works perfectly until you approach the speed of light, where new rules emerge. The physics that describes large objects works well, until you look at atoms, where uncertainty and probability take over. Each time, the previous understanding remains valid, but only within a certain range. Beyond that, something deeper takes over. So what if the same is true here? What if the universe behaves exactly as we expect, until certain thresholds are reached? Thresholds of scale, of energy, of isolation, of time. And at those thresholds, new behaviors emerge. Not contradictions, but extensions. This would explain why these mysteries cluster at extremes. Why the largest structures feel too large. Why the emptiest regions feel too empty. Why certain stars and events behave just slightly outside expectation. Because we are beginning to observe conditions where the deeper layer of reality becomes relevant. And perhaps most importantly, this would explain why we don't see clear patterns yet. Because we are only seeing the edges of that deeper layer. Not enough to map it, not enough to define it, just enough to know it exists. And that realization carries a certain quiet weight. It means that the universe is not becoming more confusing. It is becoming more complete. Every anomaly, every unexplained observation is not a failure of understanding, but a step towards something more refined. A signal that there is more to learn, more to uncover, more to connect. And as we move toward the final segments, the pace will begin to slow, not because the mysteries are ending, but because we are stepping back, looking at them together, allowing them to settle into a larger perspective. Because sometimes understanding does not come from solving each piece individually, but from seeing how they all fit within something greater than we first imagined. As we begin to slow down, to step back from each individual mystery, something interesting happens. The details start to soften, not because they are less important, but because a larger shape begins to form behind them. Subtle at first, not a clear answer, not a sudden realization, but more like a feeling that all of these strange observations are pointing in the same direction. Not toward a single explanation, but toward a deeper layer of reality. Because if you think about everything we've explored, none of it feels completely random. Each phenomenon follows rules, just not always the rules we expected. The signal had a precise frequency. The dimming star followed physical interactions with matter. The radio circles had structure, symmetry, consistency. Even the strange visitor from interstellar space obeyed gravity, just with an added effect we didn't fully understand. Nothing breaks the universe, but everything stretches it. And that distinction matters, because it tells us we are not dealing with chaos. We are dealing with complexity, a kind of hidden order that we are only beginning to glimpse, not yet able to fully describe. And perhaps the most important shift is this. We are no longer asking, what is this object? We are beginning to ask, what kind of universe allows this to happen? That question is quieter, but far more powerful, because it moves us away from isolated explanations and toward a broader understanding of how reality itself is structured. And when you approach it from that perspective, the anomalies begin to feel less like exceptions and more like indicators. Signals that we are approaching the limits of our current framework. Imagine standing at the shoreline of an ocean at night. You can see the surface, the waves, the reflections of light. Everything you observe is real, measurable, understandable within the context of what you can see. But beneath that surface, there is depth. Currents, structures, entire ecosystems that you cannot perceive directly. Now imagine that occasionally, something from below rises briefly to the surface. A movement, a ripple, a shape that appears for a moment, and then disappears again. You don't fully understand it, but you know it came from somewhere deeper. That is what these cosmic anomalies feel like. They are surface-level glimpses of something beneath our current understanding. Not fully visible, not fully accessible, but undeniably present. And this idea becomes even more compelling when you consider how often science has encountered this pattern before. The orbit of Mercury didn't quite match predictions until relativity revealed a deeper structure of spacetime. The behavior of light and atoms didn't align with classical physics until quantum mechanics uncovered a more fundamental layer of reality. Each time, the anomalies came first. Each time, they were small, subtle, easy to overlook. And each time, they pointed toward something much larger. So perhaps what we are seeing now is another version of that same moment. Not a crisis in understanding, but a transition, a phase where observations begin to outpace explanation, where the edges of knowledge become more visible, where the universe quietly reveals that there is more beneath the surface than we have yet mapped. And what makes this moment unique is not just the mysteries themselves, but how many of them are appearing at once. Signals, stars, structures, voids, explosions, ancient light, all of them, in different ways, suggesting the same thing, that we are close to something, not an answer, not a final theory, but a shift, a point where the questions begin to align, even if the answers have not yet arrived. And there is something strangely calming about that realization, because it means the universe is not becoming more confusing. It is becoming more revealing. Each unexplained phenomenon is not a failure, but an invitation, a quiet indication that there is still something waiting to be discovered, something that connects these pieces in a way we have not yet seen. And as we move into the final moments of this journey, we will not rush toward a conclusion. We will slow down. We will let these ideas settle, because sometimes the most meaningful understanding does not come from solving the mystery, but from learning how to sit with it and realizing that the unknown is part of the beauty of the universe itself. As everything begins to settle, there is a quiet shift in perspective that happens almost naturally. The urgency fades. The need to solve each mystery, to pin it down, to force it into a clear explanation, slowly softens. And in its place, something else emerges. A different kind of understanding, not one built on answers, but on awareness. Because if you think back to where we started with that single signal appearing briefly in the darkness, it felt like an isolated event. A curiosity, something strange, but contained. But now, after moving through all of these layers, it no longer feels isolated. It feels like the first note in a much larger composition, one we are only beginning to hear. And perhaps the most important realization is this: we are not observing the universe from outside. We are inside it. Every measurement, Every signal, every piece of light we analyze reaches us through a long chain of interactions, shaped by distance, by time, by the limitations of our instruments, and by the assumptions we bring with us. We are not seeing the universe as it is in its entirety. We are seeing a filtered version, a perspective shaped by where and when we exist. And that means something very important. Some of the strangeness we perceive may not come from the universe itself, but from the way we are observing it. Not as an illusion, but as an incomplete view. Imagine trying to understand a vast landscape while only being able to see small sections at a time through narrow windows that open briefly and never in the same place twice. Each glimpse is real. Each observation is valid. But without the full picture, patterns can feel fragmented, disconnected, even contradictory. That is where we are, not lost, but limited. And yet, despite those limitations, we are beginning to see connections. The same themes repeating, the same edges appearing, the same sense that just beyond what we can fully explain. There is something consistent, something waiting to be understood. And this is where curiosity becomes something deeper than just a search for answers. It becomes patience, because the universe does not reveal itself all at once. It unfolds slowly, across time, across generations, through countless observations that build on each other. The mysteries we see today may not be solved tomorrow, or even within our lifetime, but they will not remain unexplored. Each new telescope, each new method, each new perspective adds another piece to the picture. And gradually, almost imperceptibly, the gaps begin to close, not completely, but enough to move us forward. And there is something quietly comforting in that process, because it means we are not standing still. Even when we don't fully understand something, we are still learning from it. Each anomaly refines our questions. Each unanswered observation sharpens our curiosity. Each mystery becomes part of a larger journey, one that does not end with a single explanation, but continues to expand as we do. And perhaps that is the most important shift of all, to stop seeing these phenomena as problems and start seeing them as invitations. Invitations to look deeper, to think differently, to remain open to the possibility that reality is more intricate, more layered than we first imagined. Because when you remove the need for immediate answers, something else becomes visible. A sense of scale, not just the size of the universe, but the depth of it. The idea that what we understand is only the surface, and that beneath it, there are structures, processes, and connections that extend far beyond our current reach. And that realization does not have to be unsettling, can be calming, because it means there is always more to discover, always more to explore, always another layer waiting just beyond the edge of what we know. And as we move into the final segment, we won't try to resolve everything. We won't try to force these mysteries into a single explanation. Instead, we'll do something simpler. We'll let the universe remain just a little bit mysterious. And in that quiet uncertainty, we'll find something unexpectedly peaceful. And now, as everything begins to quiet down, we arrive at a different kind of ending. Not a conclusion, not a final answer, but a place where all of these ideas can gently settle. Because after everything we've explored, the signal that appeared once, the star that dimmed without reason, the circles that shouldn't exist, the structures too vast, the emptiness too complete, the ancient light that carries a subtle imperfection, the visitor that came and went, the explosion that flashed and faded, and the star that seems almost older than time itself, there is one simple truth that remains. We are still learning how to see, not just how to look, but how to understand what we are looking at. Because the universe has not suddenly become more mysterious. It has always been this way, vast, complex, layered far beyond the limits of any single explanation. What has changed is us. Our tools have improved, our reach has extended, and slowly, patiently, we have begun to notice things that were always there waiting just beyond the edge of our awareness. And perhaps that is why these discoveries feel so unusual. Not because they are new, but because they are newly visible, like stars that only appear when the sky grows dark enough. And when you think about it that way, the mysteries become less unsettling and more meaningful, because they are not signs that something is wrong. They are signs that something is unfolding, a gradual revealing, one layer at a time, as we become capable of seeing further, deeper, more clearly. There is no single moment where everything will suddenly make sense. No final piece that will lock the entire universe into a neat, complete picture. Instead, there is a process, slow, continuous, and quietly beautiful. A process where each question leads to another, where each discovery opens a new direction, where understanding grows not in leaps, but in gentle expansions. And in that process, the unknown is not an obstacle. It is the path, because without the unknown, there would be nowhere left to go, no reason to explore, no sense of wonder, no quiet curiosity that pulls us forward. The mysteries we've explored are not interruptions in our understanding. They are the reason it continues. They remind us that no matter how much we learn, the universe remains larger. And that is not something to resolve. It is something to rest within. So as you drift here, at the edge of everything we've talked about, you don't need to hold on to each detail. You don't need to remember every signal, every structure, every explanation. Instead, you can let it all soften. The idea that space is not empty, but full of things we are still discovering. The idea that reality is not fixed, but deepening as we explore it. The idea that somewhere far beyond what we can currently see, there are answers forming, slowly, patiently, waiting for the moment we are ready to understand them. And until then, the universe continues, quietly, vastly, unfolding in ways both familiar and strange. And somewhere out there, even now, another signal may be passing through the darkness. Another star may be dimming. Another event may be flashing into existence, just for a moment, before fading again. Not hidden, just waiting to be noticed. And as that thought settles, you can let your mind drift with it, outward, gently, into the quiet depth of space, where not everything needs to be explained, and not everything needs to be known. Before we end, if you're still here with me, still listening, still drifting through these quiet mysteries, gently let me know by commenting 3. A small signal, simple, clear, and unlike the others, one that returns. And now, you can rest.